Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we'd like to describe the nuclear force. It's the force that acts between these nucleons to form a nuclear matter. This nuclear force is often referred to as the strong force, and it's the third force in nature that you're probably going to learn about. You've already learned about gravitational forces. You've learned about electrostatic forces. This third force is the strong force that binds the nuclei together. And it has some rather remarkable characteristics, which we're going to describe in this lecture. So to begin, let's go back to the last slide of the previous lecture where we were discussing the binding of a neutron to a proton. That binding of a neutron to a proton to form a deuteron nucleus can be described by a potential well, very much like the potential wells we discussed when we were learning about the fundamental principles of quantum mechanics. The difference in this potential well compared to the ones we used when we discussed the hydrogen atom is the dimensions of this nuclear potential well are really small. They're on the order of femtometers, and the depths of these potential wells are really large. They're on the order of millions of electron volts. If you recall, when we did the hydrogen atom, the potential well that was appropriate for the electron was on the order of a fraction of a nanometer. The depth of the potential well that confined the electron to the proton was on the order of 10 to 100 electron volts. So everything for the nucleus is very compressed, and the depths of the well are very large. What we showed in the last lecture was that if you bring this neutron close to the proton, a new state is formed. That new state is about 2.2 million electron volts below the energy when the neutron and the proton are infinitely far apart. And the location of this state, 2.2 MeV down from the zero of energy, this is referred to as the binding energy of the neutron when it's in very close proximity to the proton. It's very interesting to take this binding energy and divide it by the atomic mass number A to get a binding energy per nucleon. And so for the case of the deuteron, right, the binding energy for the nucleons in the deuteron is about 1.1 million electron volts per nucleon present, because there's just two nucleons. You can measure these binding energies for different nuclei, and you can make a plot of the binding energy per nucleon versus atomic mass number A, and that plot is given in the next slide, and it has a very characteristic shape that tells you an awful lot about nuclei, right? So here's our deuteron. Its binding energy per nucleon is about 1.1 million electron volts. If you start to consider other elements in the periodic table, so this is helium-3, this is lithium-7, this is the lithium nucleus that has 3 protons, 4 neutrons. Here's helium-4, right? Helium-4 has a very sharp peak in the binding energy per nuclei. What you find is that if you do this if you measure these binding energies for a wide variety of different nuclei, you've got a curve that is represented by the shape of this blue line. And what you can find from this curve is a number of very interesting things. The first thing you realize is that for these very lightweight nuclei, the binding energy per nucleon is rather small, which means it's reasonably easy to separate these nuclei compared to, for instance, the case of iron. Iron 56, this is the most stable nuclei known, right? Its binding energy is up on the order of 8 million electron volts per nucleon. Of course, it has 57 nuclei, or 56 nucleons in the iron 56 nucleus. But the binding energy of each nucleon is on the order of about 8 million electron volts. If you start to look at nuclei that are heavier than iron, what you find is you find a very shallow drop-off in the binding energy. If you look at nuclei less than the mass of the iron 56 nucleus, you also find a drop-off in the binding energy per nucleon. So this iron 56 nucleus is actually the most stable nucleus that we know of. And it's a really interesting question to ask how these different nucleons bind together to form these different nuclei, and why these nuclei have different binding energies. And I like to try to motivate that discussion by just doing a very simple calculation of the forces that you might expect to act between the different nucleons that form a nucleus. And so that calculation is sketched out in this slide, where I show a schematic picture of a nucleus. This nucleus contains protons, which are positively charged. It has a number of neutrons that are distributed among the protons, right? And if you ask what are the forces that are acting on these nucleons, well, the simplest force to calculate is the electrostatic force between individual protons. The neutrons are electrically neutral, so we don't know how they electrically they would not interact with a proton. There would be no net electrostatic interaction. But for sure, there's a repulsive force that acts between protons that are confined to this nucleus. And we can estimate that electrostatic force. We go back to Coulomb's law, right? We have to use the separation between the protons, and the separation between protons and the nucleus is on the order of 2 × 10⁻⁻15 meters. The charge on the protons is 1.6 × 10⁻19 coulombs. And when you evaluate that electrostatic force, what you find out is, of course, that it's repulsive because the protons have the same charge polarity. But you find that when you evaluate this number, you get a number that's on the order of 58 newtons of force, repulsive force, that are pushing these protons apart one from one another. And so then you wonder to yourself, well, you know, if you've got this massive force acting over this very, very tiny distance, a few femtometers, how in the world does this nucleus actually stay bound together? And how does it produce a binding energy per nucleon that gives rise to this wide range of nuclei that are in fact stable? And the answer to that question is there must be an additional force in nature that acts to bind these nucleons together, and that additional force is referred to as the strong force. And so what we now understand is that when you bring these nucleons close enough together, this nuclear force, or this strong force, is a very attractive, very strongly attractive force that causes these nucleons to bind together. And the attraction exerted by this strong force must be strong enough to overcome the electrostatic repulsion that we estimated in the previous slide. So what you tend to find is that for small nuclei, the number of protons and the number of neutrons tend to be about equal, right? And what we now know is we know that these nucleons exert very strong nuclear forces between the nucleons. And in fact, the neutrons are incorporated into the nucleus in order to help bind the nucleus together, right? They help overcome this very strong repulsive force between the positively charged protons. As the mass of the nucleus increases, right, what you find is that more and more of the protons start to reside on the perimeter of the nucleus, and there's not enough nucleons present to balance the strong electrostatic repulsive forces between these exterior nucleons. And so as a result, you've got to start to pack more and more neutrons into the nucleus in order to counteract this strong repulsive force. So you have to make the distinction between interior nucleons, where for instance you might have a proton that's surrounded by a certain number of neutrons, and the neutrons and the protons are all being attracted one by another by this very strong nuclear force, right? You have to distinguish between those interior nucleons and the exterior nucleons. The exterior nucleons require additional neutrons in order to exert a force that overcomes this repulsive force between the individual protons. So what you're going to see is when we start to look at systematics of nuclei, you're going to see that as the nucleon number increases, the number of neutrons compared to the number of protons is also going to increase. And so the heavy nuclei are going to be neutron rich as a result. Can we say something qualitative about the nuclear force that must be acting between the protons? Well, the answer is we can make some qualitative arguments, right? And I'd like to do that in terms of this particular slide here. So what I do is I plot the force as a function of a proton-proton separation. And let's first just consider the electrostatic force that interacts between the protons. The electrostatic force is going to be given by Coulomb's law, and it's going to be represented on this plot schematically by this 1 over r squared behavior, right? This is going to be a repulsive force, and so I make repulsive forces positive in this chart. I make attractive forces negative in this chart. So if there's just an electrostatic force that interacts, that causes the protons to interact, there would be this very strong repulsive characteristic, varies as 1 over r squared. There must be a very strong nuclear attraction exerted by this strong force, and that strong nuclear attraction is represented in this plot schematically by this dashed line. Now, to the best of my knowledge, in contrast to the electrostatic force between charged particles, the equation that governs this strong nuclear attractive force is not well known. And for that reason, I just indicate it schematically as an attractive force that acts over a very small distance on the order of femtometers. This strong nuclear attractive force has to be added to the Coulomb electrostatic repulsive force to get the net force. And the net force is going to then look something like as shown by the solid red curve here. When the two protons are far apart from one another, they feel this Coulomb repulsive force. But as you force those protons closer and closer to one another, this strong nuclear attraction takes over and overcomes the repulsive electrostatic force and produces a net force that binds the nucleus and actually causes the nucleus to exist. If you continue to push the protons closer and closer to one another, this nuclear attractive force has to eventually become repulsive. That has to be so because if we find that the nuclei do have a finite radius, if there was no strong repulsive interaction when the nuclei get closer to one another, then you would expect the nuclei would just somehow collapse into literally a point in space, but that doesn't happen. So there has to be a very strong repulsive component that sets in when the nuclei get extremely close to one another. So qualitatively, this describes the nuclear force, the strong force that interacts between nucleons. If you have a proton interacting with the neutron, the only thing that's different is this electrostatic repulsive force isn't there. And you're then left with this strong nuclear attractive force by itself. When you have a proton interacting with a proton, you've got this Coulomb barrier that sets up, prevents the two protons from approaching one another very closely. But if they can get close enough, they overcome this Coulomb barrier, and they are, in fact, influenced by this very short range, very strong nuclear attractive force. Now, this picture of forces at the nuclear level has led to a reinterpretation of forces that I like to try and describe. And I'd like to contrast the field representation that you're familiar with from electrostatic forces with this so-called vertical particle representation, which is the current model that's used to understand the force between elementary particles. So first, let's review very quickly the electrostatic field representation of a force. The idea is pretty simple. First, you've got a charge in space. Let's say it's an electron. This electron generates an electric field E that fills all space, right? And the formulas that allow you to calculate the electric field are well known and well described from your courses in electricity and magnetism. If you bring an additional point charge, let's say you bring an additional electron into a region of space where there's a net electric field, then this point charge feels a force which is just given by the charge Q. In this case, it's minus the charge on an electron times the electric field E that exists at this particular point in space. And of course, the electric field is defined in such a way that you recover Coulomb's law when you multiply this charge E times the electric field E. The force of interaction between these two electrons is then just K Q1 Q2 over R squared in the radial direction. So that's the field representation of forces. The virtual particle representation of forces is something that we discussed in last week's lectures. This is the idea that two particles can exchange a virtual particle, and this virtual particle actually causes a change in momentum between the two particles that are interacting. And this change in momentum can be, when divided by a time interval delta t, is equivalent to a force of interaction between two particles. So for instance, if we have two electrons that are approaching one another, these two electrons can exchange this virtual photon. This virtual photon then gives rise to this exchange of the virtual photon gives rise to a repulsive force, which would then cause these two electrons to repel one another. And when you discuss a force in terms of the virtual particle representation, the range of the force, right? The range of the force is going to be inversely proportional to the mass of the particle that's exchanged. So since the photon mass is zero, right? Photons don't have any mass. This is an infinitely ranged force, and these two charged particles would interact even if they're in principle infinitely far apart. So examples of this are given in this slide, right? In this case, we've got two electrons interacting with one another. The interaction occurs by the exchange of this virtual photon, and the exchange of this virtual photon causes a change in the momentum of these two electrons, which then cause them to actually repel from one another. A more interesting example is given by considering the exchange of a virtual particle when a neutron and a proton interact with one another. So here we've got a neutron approaching a proton. When this neutron and proton get close enough to one another, they exchange something called a pi meson. the mass of this pi meson is about 1/7 the mass of the neutron and the proton, right? And it's the exchange of this pi meson and the change in the momentum that's exerted on these two particles that cause them to interact and actually produce an attractive force that causes these two particles to be attracted towards one another. So this whole idea was developed in 1935 by this Japanese theorist by the name of Yukawa. It turned out this idea of a virtual exchange of a particle between these fundamental particles, the neutron and the proton, that was finally, the pion was finally discovered in 1947. Right, and Yukawa got the Nobel Prize in Physics for 1949 for developing this concept of an electrostatic, or of a virtual exchange of particles to describe nuclear forces. Now, the nature of these nucleon-nucleon interactions have been investigated probably for 50, 60 years. And basically, all of our understanding of these interactions come from these collisions between neutrons and protons, or protons and protons, right? So for instance, by producing high-energy particle accelerators that cause protons to interact with protons, neutrons to interact with protons, by taking pictures of these interactions using photographic plates. That's what was used in the early days. Photographic plates would capture the tracks of these particles as they interacted, right? You could actually study the angular distribution of the interaction. So in this particular plate, right, you've got a proton that's approaching another proton, which is essentially at rest at this point. After the interaction has occurred, you can see two tracks that emerge. These two tracks can be then analyzed for their energies and for their angular distributions, and that allows you to actually investigate both the range of the nuclear forces and allows you to determine some of the characteristics of the nuclear forces that we referred to in earlier slides. So the one calculation that I like to run through here is the calculation of the range of the nuclear force. This is an interesting idea because it allows you to correlate the mass of these mesons that are exchanged between protons and neutrons. Allows you to correlate that mass with the range, the distance in space over which these protons and neutrons interact one with another. And this range of the nuclear force comes about by referring back to the Heisenberg uncertainty principle for energy and time. And basically what this uncertainty principle in energy and time tells you is that if you want to measure the energy of a quantum system within an accuracy of some parameter delta E, you're going to require a time interval greater than delta T, right? And delta E and delta T are related by this familiar Heisenberg uncertainty principle argument, which says delta E, the accuracy of the energy that you measure a system times the time delta T over which you measure the energy of that system, that quantity has to be greater than h bar by 2. And the parameter delta E that appears in this equation is set equal to the mass of these virtual particles. In the case of a proton-proton or proton-neutron interaction, that would be the mass of these pions, right? So the energy uncertainty is associated with that mass, m sub p times c squared. That gives you a time interval, delta t, and that time interval turns out to be just h bar over 2 times the mass of the pion times c squared. The force range is then taken by multiplying this time interval delta t times the speed of light, And that then gives you an estimate for the range of the force over which these two particles interact one with the other. You can calculate, you can evaluate this expression for the range of the force, and you end up with expressions that are on the order of 10 to the minus 15 meters, femtometers. So this uncertainty principle argument gives you a qualitative way for understanding why these interaction distances are so small. The reason the interaction distances are so small is that the mass of the particle that's exchanged between these nucleons is large, right? So the range of the force is inversely proportional to the mass of those mediating particles. So this whole idea comes out of this virtual exchange of particles that describe forces between these nucleons when they start to interact. So from these scattering experiments, you can begin to infer the shape of the nuclear potential well that describes the quantum states for these nucleons when they're trapped inside of a nucleus. And I just try to qualitatively show you the results that have been obtained over the years, right? There's two plots for the potential energy of the nucleon when it's confined to a nucleus. On the right-hand side of this plot, we have the potential well that a proton would experience or would feel. On the left-hand side of this diagram, we show the potential well that a neutron might experience when it's trapped inside of a nucleus. Right? The force range, R, is given by this simple argument that we discussed in the previous lecture. The mass of these particles that are exchanged in the process of two nucleons interacting, those masses of those particles are obtained from scattering experiments, right? Occasionally you will actually detect one of these mesons as they're exchanged back and forth between, let's say, a proton and a proton when they interact. By measuring the mass of that exchange particle, you can then infer the range, the force range, or the dimensions of this nuclear potential well. There's for the case of a proton, right, you have to include this Coulomb repulsion term, right? For the case of a neutron, the neutron turns out to be bound a little bit more stably than a proton in a nucleus. It's actually got a deeper well associated with it because it doesn't experience this strong Coulomb repulsion. So I put in the appendix a discussion of the analytical form, or one model for the analytical form of these potential wells. You can take a look at that if you're interested. But the important point to take away from this lecture is that this strong nuclear force that interacts between nucleons produces a potential well, and when you start to fill this potential well with either protons or neutrons, there are allowed energy states that come about. These allowed energy states are just like the allowed energy states, or very similar. They're not just like, they're very similar to the allowed energy states for electrons when electrons are confined to, let's say, a hydrogen atom. And this is like the current understanding of nucleon states in a nucleus, right? It's the energy, allowed energies for these different quantum levels that develop when you trap a nucleon in a region of space that's given by this parameter R. So in the next lecture, we'll describe very briefly some of the features of the energy states for these nucleons that have been uncovered. We won't go into nearly the detail that we did when we discussed electron states in solids or in atoms. But it's interesting to see how the allowed energies of nucleons are different than the allowed energies for electrons. Qualitatively, there's a lot of similarities, but there are fundamental differences between the two systems. and we'll take that up in the next lecture. So that's all I got to say about this particular topic. Come on back and we'll talk about the allowed energy states in these nuclear potential wells.